Okay, so chapter 3, we're going to talk about carbon first, and then I split the rest of these notes up into one about functional groups, and then I'm going to do one on carbs by itself, one on lipids by itself, one on proteins by itself, and one on nucleic acids by itself. So all in all, there should be 5 videos for this chapter.
Bruh.
But because I've cut them up so much, it should not be too long for you to like sit through each one.
Ain't nobody got time for that.
So let's start with just talking about carbon. Alright, so the first thing that you need to understand is that living things are made primarily from carbon. Like, carbon is the central atom in a lot of the molecules that make cells. So molecules that contain carbon are referred to as organic compounds. So again, organic compound is just a compound that has carbon. Alright, so there are some molecules that are critically important for us to be able to survive and for other living things to be able to survive. So those different molecules are placed into 4 categories. The first listed here is carbohydrates. The second is lipids, which you know as fats. By the way, carbohydrates, people tend to call them sugars. But we'll go over like structurally how they can differ from one another. So lipids are fats, proteins, and then nucleic acids. So nucleic acids, that is the Na in DNA, and when we go to that particular lecture, I'll tell you more about nucleic acids and their structure. So the authors of the text refer to the first 3, so carbs, lipids, and proteins, as macromolecules. And one way to remember what that means is just macro means large, and you already know what a molecule is, so macromolecules are large molecules. Oh, there's one other thing that I did want to say on this slide. So one way to think about this is when you look at the back of a food label, you see these things listed, like carbohydrates are part of like the nutritional label. They'll tell you how many grams of carbs are in whatever it is you're eating. Same thing with lipids and proteins. Nucleic acid content is not, okay, I'm sorry for that outburst. But anyways, so nucleic acid content is not listed. However, the things that we eat come from other living things, so they're going to contain nucleic acids as well. It's just not something that needs to be listed. So not only do we eat these things, they're also the things that make us up. If we need to replenish something, the elements that we get from the macromolecules are the source of making new cells or making whatever more you need to make.
You see, you are what you eat, from your head down to your feet. Things like...
All right, so here's a picture of a protein.
Look at this. Somebody come look at this.
And I know it looks crazy. It looks like ribbons, maybe like some stretched out plastic cord, but all of this will make some sense once we dig into specifically proteins. Okay, so first thing to remember, carbon, which is the central atom, and all of the molecules that we're going to be discussing in chapter 3. It has a valence of 4. So what exactly does that mean? It just means that if we were to count the electrons that are on the outermost shell of carbon, you would find that there are only 4 electrons there. So how am I coming up with this number? So briefly, I'm just going to show you how you could represent this on a piece of paper and visualize it. So here's the symbol for carbon. It's just a C. And you'll notice that carbon's atomic number is 6. You should look at a periodic table to verify. So if I wanted to display what the valence was for carbon, I could start off by just drawing the first ring, and the maximum number of electrons the first ring can hold is 2. So 1 electron there and 1 there. So there are the 2 electrons for the first shell. The second electron shell can hold up to 8 electrons. But in this case, the total number of electrons that we want to display is 6. So that would mean we need to add 4 to this next shell. So 1, 2, 3, 4. And if you were to count all of the blue lines I just made, you come up with 6. So what does that mean? Remember, I just said the first shell can hold 2, the second shell can hold up to 8. It's just a rule that you have to remember. So since that is the way it is, it leaves room for 4 other potential places where another atom can combine with carbon. So the question that I think some people may have is like, how do you use the periodic table to tell the valence of electrons? And there is a small trick. It's not really a trick, it's just a way of like looking at the periodic table. So we can look at the elements in groups. And by group, I mean like you're looking straight down the column. So we're going to look at the first column, which is here. So we're talking about hydrogen, lithium, sodium, potassium, rubidium, so on and so forth. Notice that at the very top, the group number is 1. That just so happens to also be the number of valence electrons, or the valence number for every single one of the elements in that grouping. And the next one, group 2, all of those only have 2 electrons. So their first shell is full. We don't look at this in the center. We skip over it. Okay, so we're not going to worry about the center right now. But what we are going to do is we're going to keep on counting across the groups minus the part in the center. So we're going to pick up right here where boron, aluminum, where they are. So this one says 13 at the top, but we're looking at valence shells, remember, or valence electrons on a electron shell. So this one is going to be 3. This one is 4. So carbon's row is 4. Nitrogen's row is 5. Oxygen's is 6. 7 for the row with fluorine, or column, excuse me, not row, column, with fluorine, and 8 for the one with all of the noble gases, helium, neon, argon, so on and so forth. So just look at the group number at the top of each column, and that is how you can tell very quickly what the valence number would be for an atom. Alright, so this illustrates exactly what I just was saying. You should still have a periodic table out right now and be looking at it. Notice that hydrogen is the first element on the table. It has 1 as its atomic number, which means it has 1 proton, and the number of protons as elements are on the periodic table equal the number of electrons. So there's 1 valence for hydrogen. Why is it 1? Because it already has 1 electron there, and it can take a second one. Okay, so now let's look at the valence for oxygen. How are they coming up with 2? The first shell is full, has 2 electrons. The second shell has 6 electrons. So oxygen could bond with something 2 more times, and then its valence shell would be full. So the 2 spaces where these can bond would be like here and here. For nitrogen, they're saying the valence is 3. I think you guys can figure out why that would be 3. Go ahead and count the first ring. So 2 here, and then here there's a total of 5. And 8 minus 5 is 3.
You guessed it. You was right.
Last one is carbon. This is the one that we're talking about, special one, and it has a valence of 4. Alright, so because carbon has these 4 valence electrons, let's first establish what the word valence means. It's of Latin origin. It translates roughly to power, or being like strong and well. And if you think about the elements in that way and their valence shells in that way, it makes more sense so that you can figure out the behavior of these various elements. Like usually if there is 1 electron short of a valence being full, that atom is more likely to be ionic, and it's more likely to take an electron from a cation. So they would be anions in this case. Let me see. Okay, so with carbon having this valence of 4, it gives it 4 places to hook up to either other atoms, or just 4 places to hook up with itself if it wanted to. So this 4 is, it's perfect. It's right in the middle of 8. So carbon is not likely to give up anything. Carbon is not likely to steal anything. Carbon likes to share. Okay, so because of the way carbon attaches to specific elements like hydrogen, you get these shapes that are very common. And if you were to look at this with the 3D modeling kit, which we do have in class, I will try to give you guys the opportunity to build something and then see what it looks like 3-dimensionally. It helps with your perception of the molecule in space. So the first one, tetrahedral shape, methane is CH4. They're showing you that the carbon is bonded to 4 other hydrogens for methane. Ethane, 2 carbons, and then each of those carbons have 4 places where they are sharing these electrons. The last one, ethylene. There's 2 carbons, and in the center what you see is a double bond right there. So that double bond counts for 2, let's just say two electrons being shared back and forth. So you would count each carbon as having 2 bonds with the other carbon, and then 2 bonds with the 2 hydrogens on the side. So the usual suspects for carbon covalently bonding with other elements are hydrogen, which you just saw, oxygen, and nitrogen. outside of that, you don't really see carbon bonding with too many other things as far as like biochemistry goes. So we're going to stick with these 3 other elements, and you might recall that they are essential elements from chapter 2. All right, this is an example of carbon dioxide. This is what it looks like. What you need to see here is the linear way in which this is laid out. Those 2 double bonds that the carbons are sharing with the oxygens on, or the carbon is sharing with those 2 oxygens on each side of it, it makes the molecule flat. And this bonding, by the way, is covalent bonding. Because remember, carbon is not stealing anything, and carbon is also not giving up anything, but it is willing to share. So covalent bonding is the sharing of electrons. Here's a picture of what it would look like if you were to draw like a Lewis dot structure of it. Or actually, this is like a Bohr model of it. That's not important. Don't worry about looking up what I just said. So again, first ring always has 2, and then you'll notice that the second ring, oxygen and carbon, they're sharing those electrons. So they're not all just in the center there. What's actually happening is these electrons kind of whiz around this entire molecule like it's a racetrack. So you would see behavior like this if you could actually monitor the electrons moving. It would be like a loop-de-loop, you know, like at any given time on that second electron shell, those electrons could be floating anywhere around the 3. But the first shells are intact. They keep the 2. All right, here's another one. Again, you have the carbons. If you were to go ahead and count around the valence shell, the last valence shell, you'll see that there's 8 electrons moving around there. And the first orbital is always occupied with 2. In the case of hydrogen, hydrogen is sharing its electron with carbon, and carbon is sharing one of its electrons with the hydrogen. So everybody's playing nice together. All right. So because of the way that carbon can bond, like the 4 places it has to bond with something else, you can get a lot of variety in the type of molecule that is created. So 2 ways they can vary. Carbon can vary in length, and it can also, a carbon-based molecule can vary in length, and then it can also vary in shape. All right, so here are examples of carbon bonded to carbon, and they go on for some time, and they make like a chain kind of. So you see ethane and propane there. The next one, they're showing you when you branch carbon, what it ends up looking like. So here, this is like a straight chain, but then this one is branched. For C, they're showing you like there's these double bond positions. They can move, and it changes the molecule. And then whether or not it's a ring, so if the carbons are in a ring structure like a benzene, benzene, then that's the configuration that you would see. And benzene would have a different property than cyclohexane, and it just is dependent on how the molecules are attached to each other. Really, that's it. So with the benzene, you have some double bonds in between the carbon molecules on this ring, but in the cyclohexane, there is no double bonding happening. You have like just single bonds and then a bunch of hydrogens attached. So I do know that there were some people in groups earlier that did not know that these points, like on the rings, I'm trying to draw it as neat as I can, but all of these like corner edges, people did not know that those were actually carbons. So I want to make that very clear. When you see this kind of like line shape thing, or in this case a ring, Those pointed edges are carbons with hydrogens attached. And so that's another reason why it's really important to understand how valence works, because you can tell whether or not an atom is like, if it's sharing enough, is it complete, is it going to ionize, that kind of a thing. The last thing I want to do is zoom in on each of these individually. So if you look at the length one up here at the top, they're showing you ethane, there's 2 carbons bonded to each other. Propane has 3 carbons bonded to each other. Butane has 4 carbons bonded to each other. And then the last one, 2-methylpropane, it also has 4 carbons bonded to each other. However, this 2 in the beginning of the name of this molecule lets you know that at the second carbon there's some branching that is occurring. So it's not linear, it goes across, and then there's also one attached, not in straight formation. Notice that all of these end in ane, A-N-E, propane, methane, butane, blah, blah, blah. All of those A-N-E endings simply mean that the carbon-carbon bonding is like the central focus of the atom. All right, here's the double bond positioning. You'll notice now that the A-N-E ending has turned into an E-N-E ending. And again, the numbers here are simply designating where the double bonding is occurring. So for 1-butene, this is telling us that there's a double bond involved with that first carbon on the ring. And then in 2-butene, you know, you have to go over 1, 2 to get to the double bond. Let me see, where else? So benzene is another one where there's some double bonding happening. We've already talked about that one, but let's talk about what the E-N-E ending means. E-N-E, or ene, tells you that there's going to be a double bond in the atom. Excuse me, not in the atom. There's going to be a double bond within the molecule that you're looking at. And yeah, so that's all you need to know about that. Let's keep going. All right, hydrocarbons, that word breaks down exactly into what it is that we're talking about. So hydro, you'll notice, sounds like hydrogen. And then the carbon part is carbon. So hydrocarbons are just a bunch of carbons linked together with hydrogens filling up the rest of whatever bonding is available to happen. So now we're going to move a little bit away from just the focus of carbon and very quickly just discuss isomers. Isomers are molecules that have the same number of elements and the same elements, but they're structurally different. So there are different types of isomers that are possible. You can have a structural isomer. So this is just an isomer that is different in the way that the bonds are arranged. So they define it for you right here on the slide. Structural isomers differ in the covalent arrangement of their atoms. There's also something called cis and trans isomers. I want to show you visually what they look like, but here is a definition of what they are. They're carbons that are covalently bonded to the same atoms, but they differ in which side of the atom they differ in which side of the element that they are on. So this will make sense when I show you an image. All right, an enantiomer, they're isomers that are mirror images of each other. So if you think about, like, when you look in the mirror at yourself, your reflection is like backwards. And by that I mean, like, you know, if you had on a t-shirt with words and you were to look into the mirror, it looks opposite you. So the way to think about this is with your hands. That's the best way to do it. So here's a picture of what I was just saying about the way your hands are facing in enantiomers. Before we go look at that, I know for a fact that the next 3 slides are gonna emphasize A, B, and C individually. So I'm gonna go to the next one and I'll talk about them with a picture up. So structural isomers, they give us an example that we've already seen with the 2-methylbutane, where the branching kind of happens at the second carbon here. Pentane is just the straight line. So you notice that if you were to count the number of carbons in both of these, they're identical. If you were to count the number of hydrogens in both of these, they're identical. The only difference is structurally where one of the carbon-carbon bonds is happening. So in pentane, again, it's carbon-carbon-carbon-carbon straight across. There is no branch section, but the 2-methylbutane is an example of branching. And that changes the property of this particular molecule. So cis and trans isomers, this is what I meant by when I said there's going to be atoms that are like on opposing sides of the molecule, or they can be on the same side. So for cis and trans, what I usually do to keep it straight in my head, I always go like, I have sisters, so I say my sisters are on my side. Notice that the cis ones are on the same side, but the trans ones are flip-flopped. All right, here are the enantiomers. So these look exactly the same, but the problem is if you were to lay them on top of each other, kind of like your hands, if you're looking at the back of your hand when you do this, lay your 2 hands on top of each other. Your thumbs are pointing different directions. Your pinky finger and your ring finger match up. Your middle finger and your ring finger will match up, but then like that's it. There's no other, sorry for the door closer again. There's no other way for me to show you that really quickly with your own hands. That's the best way to look at it. So when we do, I want to pull out model kits just so you guys can like piece these together and you can see what they look like, and that's it. So that's the end of this, and you have a few more to come.